So, good morning, everyone. I'm hoping you're enjoying your KubeCon in Barcelona and getting in all the extra exercise, walking from the keynotes to the different speaking sessions. So, first off, before we begin, in an interesting example of how consistency in distributed storage is a challenge, there seems to have been some logistical issues where the app has been showing that our session is in G1 and the web session has been showing that we're in G2. So if you're here for the Open API, you're in the wrong place. That's in G2. All right. So one other thing that you might notice is in the schedule, this was originally supposed to be around the CNCF storage working group, but just hot off the press, the storage working group is transitioning to to a SIG. So I'm going to spend just a little bit of time talking about the new CNCF SIGs, which have just been formalized, and give you a little bit of background on this. So all of the information is on the CNCF GitHub, but for background, the SIG is here to help scale the CNCF. So over the last year, we now have over 400 organizations who are members of the CNCF, and another 85, maybe 90 end-user organizations have also joined. And the number of projects that have been added to the CNCF and need attention and help and coordination has been growing. So the idea behind the SIG is that this helps the TOC, which is the Technical Oversight Committee that manages these projects in the CNCF. It allows them to scale. So what the SIG is here to do is to meet effectively the needs of you, the end users, right, and figure out the types of projects that are going to be needed in a cloud-native environment, and working on reviewing and providing help to the TOC on a number of different projects which fall into different categories. So one of the key things that the SIGs are going to be working on are handling the different projects. So working with the projects, reviewing the projects, providing feedback for the TOC, but also, more importantly, actually working with the projects to help them present and get ready to join the CNCF. We also have a responsibility for helping the end users. So things like providing up-to-date information, perhaps white papers, and we'll talk a little bit about some of the information that we've generated in the storage SIG in a minute. And we're also here to look at gathering information from the end users so that we can provide the right feedback to the TOC and to the projects to help guide where these projects go. And finally, everything that the SIG does is completely open. So we have open meetings. Everybody's free to join. There are open meeting notes, open mailing lists, etc. And as trusted advisors to the TOC, we have a number of technical leads and sub-projects that form within the SIG to perform particular functions to help the TOC do their mandate. With regards to the storage SIG specifically, our mission is to provide all of this information to the TOC, but also to help them maintain the health of the CNCF storage projects specifically, and we'll talk a little bit about those in a second. And we're constantly looking for additional projects to add in to the CNCF. So what we're specifically looking for are understanding the different storage approaches, providing information for these projects. And one of the key things that we generated last year was the CNCF storage landscape white paper, which covers a whole plethora of information around to help end users understand the differences and the different attributes in different storage environments. And working with a number of different storage systems that include both traditional volume-based systems like block stores and file systems, but also API-driven systems like object stores, databases, key value stores, etc. And fundamentally, just in order to sort of bracket that scope, we're looking for storage systems that satisfy the CNCF cloud native definition, right? So we're looking for storage environments and storage projects that work with microservices that are scalable, that have APIs, that are declarative, and that are automatable and interact with orchestrators. So we're not an island. We work with a number of other groups in the ecosystem, and in fact, there are overlaps in terms of membership between the CNCF Storage SIG and some of the other organizations that work with the projects related to storage. Obviously, the Kubernetes Storage SIG is a big driver in this area. We'll be looking to work very closely with them, and actually what the lead from the storage SIG actually works with the CNCF storage SIG very well too. We're also working quite closely with the CSI team. So the CSI is the container storage interface, and this is the standardized interface that different orchestrators can use to interact with storage systems. We'll also be working with the CNCF storage SIG, the CNCF security SIG, and as soon as it forms the app SIG, to work in terms of how different storage systems interact with different applications in real life. So in terms of the operating model, the SIG is formed with a number of chairs and a number of tech leads. These are the current chairs that have been voted in and tech leads that have been voted in by the TOC today. In fact, today the vote was cleared. So this is hot off the press. The storage SIG meets every second and fourth Wednesday of the month at 8 a.m. Pacific time. So that's 4 or 5 p.m. European time. The details for everything that this SIG storage does for the CNCF are available in that GitHub repo, and I've posted some links there to cover the meeting minutes that cover some of the things we discussed. It's probably important to note that everything that the SIG does is vendor neutral. We have a lot of different vendors that work with our group, including some of the names listed below. But we also have a number of individual contributors and independent contributors that help work with the projects that we're working on. So I'll talk a little bit about why storage is so critical for cloud native. In the environments, in the cloud native environment, a lot of work has gone into making applications portable, declarative, and platform agnostic. So containers give you the ability to contain an application and all of its dependencies and provide the ability to make an application portable. Orchestrators like Kubernetes help you to abstract away the infrastructure and give you the ability now to declare how your application needs to run. But it kind of does a really good job of sort of playing Tetris with your workloads, right? So it figures out the best places to put your applications based on what you declare in your application in terms of CPU, memory, and say network requirements. But just as important are the stateful applications, right? So no application really doesn't, there's no such thing as an application that doesn't store state somewhere. Every application to be useful is storing state. Now that can be something that can be a service that lives within your orchestrated environment, your Kubernetes environment, but it could also be using services that live outside of that environment. So the cloud native storage that we're talking about is effectively supporting the portability aspect, right? So we want you've done all the hard work to make your applications portable by putting them into containers and microservices, for example. You've done all of the hard work to make your applications declarative and allow orchestrators to scale your applications and automate your applications. And therefore, being able to apply that portability to stateful applications and providing the means to interoperate with different storage environments is kind of the next logical step there. So the goal of storage in the CNCF is effectively to drive this ubiquity of cloud native computing, and to do that, we have to have a strong storage ecosystem, a strong set of projects that are both vendor and platform neutral, and provide that interoperability for your applications. So during the life of the working group previously and now the SIG, a number of different projects have presented, including some very well-known ones like CSI and Rook, for example, and a number with collaboration with the working group and with the talk, a number of these projects have been accepted. Rook initially as a sandbox project, and which is now graduated to an incubating project. Vitesse has been accepted as an incubating project. TIKV was a sandbox project and was just announced as an incubation project today. And OpenEBS was accepted as a sandbox project. And just a bit of background on some of those projects that we're looking at. Rook provides an operator and framework to help automate the deployment and management of different storage systems, but primarily Ceph. Vitesse is a distributed database project which originally started life in YouTube. TIKV is a distributed key value store with a lot of advanced functionalities, and it's also used as the basis of TIDB, which is a database that sits on top of that. And OpenEBS is an open source storage project, storage volume project. So we talked a little bit about how we can help provide information to the community. And one of the things that we worked on last year and published the draft back in KubeCon Seattle was the storage landscape white paper. The white paper is there not to recommend any specific systems. In fact, it doesn't specifically go out of its way to list specific storage systems. But it's there so that people can get a better understanding of the available solutions out there in terms and the attributes and the layering of these different storage systems. And this is important because with the advent of cloud native, the way that people interoperate with storage systems is changing. Storage systems used to be the sole domain of an infrastructure team. But more and more, and those storage systems were often very static in what they were offering to application teams. So very often application architects or developers had to develop an application to fit around the storage system. More and more in cloud native environments with such a rich offering of both cloud services and software and hardware offerings, we have a new paradigm coming where developers can understand the attributes of their environment and therefore choose a storage system or shape the storage system around the applications of the requirement. So effectively, this is empowering the developers to make some of these decisions, and that was the objective of the white paper. So the white paper had a number of authors from the CNCF SIG or working group, a lot of these names you'll recognize as contributors or working on other projects like CSI or etcd, for example. And what we cover in the white paper is what's effectively inside a storage solution. So we wanted to look at the different interfaces that different storage systems have, and look at the different attributes of a storage system. So we focused on 5 main attributes: availability, scalability, performance, consistency, and durability, because these are the things that a lot of people perhaps don't fully understand or maybe take for granted in some cases. So the storage attributes that we were looking at kind of cover functionality or capabilities of different storage systems. So when we're looking at things like availability, we're often thinking about perhaps redundancy, but it also covers aspects like how does data fail over, how does a pod continue to access the data as during failure scenarios, for example, as well as the more traditional redundancy and data protection. Again, scalability is another one of those topics which can be measured on a number of different axes. So in some cases, it might be important to have a storage system that can be accessed by hundreds or thousands of clients. In other cases, it might be about the capacity of the storage system or the throughput or the number of operations that the storage system can handle. And then obviously, performance is always a big factor. That is something which drives a lot of decisions. And again, sometimes it's important to have to look at storage systems from a latency perspective, where the way you consume the storage is a very big factor. Other times it might be a case of understanding how the storage can provide the throughput in terms of megabytes per second or IOs per second. And those sort of functionality could translate into how you architect your cloud environment or your on-prem environment. Consistency is a thing which comes up very often in storage system evaluations. So many distributed systems take a number of different compromises in terms of the types of attributes that they support. So for example, some systems might optimize for scale and some systems might optimize for performance. Invariably, that leads to compromises on the types of consistency that those systems can support. So the more moving parts you have in a system, the more likely you might have delays to consistency. And those delays can be measured across 2 axes. One is sort of the time it takes between actually committing data to a storage system and the storage system actually acknowledging that data has been committed. And it could also be around the time it takes between data being committed to a storage system and the correct data actually being returned on subsequent reads. And then finally, the other important thing to consider when looking at cloud-native environments, especially when we're looking at hybrid clouds and perhaps different managed services, it's really important to understand the durability of your systems, right? So having redundancy to help with your availability is one aspect, but where your data is protected, which geographies the data is copied to, how many failures can you tolerate before the data is lost, etc. And then also, some of the more low-level things, so things like bitrot. So, what do you do when physical media starts to fail? So these are all things that are considerations when you're considering different storage systems. Of course, cloud-native storage systems come in all shapes and sizes and can be instantiated and deployed in a number of different ways. There are traditional hardware solutions which get deployed on premises in your data center. There are software options which provide the data services and the functionality of a storage system, but don't actually mandate specific hardware requirements, which obviously mean that they're probably a bit more portable than the hardware solutions. And then there's a whole plethora of cloud services that can be consumed from private and cloud and public cloud providers, covering everything from volumes to databases to other services. So we'll talk a little bit then about how we consume the storage. In a cloud-native environment, there are a number of different data access interfaces. So a workload can be talking to a storage system, and in what we define as sort of two major buckets. The first being volumes, and the second being what we call APIs. So volumes are perhaps the more traditional type of storage, so things like block stores, file systems, shared file systems, etc. APIs covers everything that you access traditionally over a network to a well-defined API, so things like object stores, key value stores, but also things like databases. So the cloud-native storage mandate also covers the uses of things like databases, which you might not necessarily automatically associate with storage, but databases are just another way of persisting data. It's probably fair to say that in a lot of the orchestrated environments, volumes have the more mature interfaces and the more mature options in terms of abstractions. So Kubernetes has, for example, a rich set of drivers and interfaces like CSI, which we'll discuss in a minute, that allow native interaction with a whole number of different storage systems. And there are a number of projects which are being built that help provide abstractions over some of the API-driven storage mechanisms. So a couple of the projects that we've looked at recently, so projects like Rook, are introducing abstractions to help automate and manage things like databases, and also again, it's kind of the early days for them, but we're also seeing a lot more Kubernetes operators. So Kubernetes operators are effectively pieces of code that help automate the management of something stateful like a database or perhaps a storage system within a Kubernetes environment. So different volume access interfaces traditionally have different attributes. And what we'll discuss now is what is the most generally accepted attributes of these different environments. But of course, one thing that we'll discuss in a minute is how the different storage layers in a storage system can contribute to how the attributes of these different data access interfaces can be affected. So, in many cases, block systems are most suited for things like availability and low latency, but they're less suited to, for example, things like scaling, and they really don't do very well with sharing data with multiple workloads, for example. Whereas file systems are great at sharing data with multiple workloads and typically very much optimized for throughput. Object stores tend to be very optimized for capacity and durability and availability. So object stores work. Typically, object store architectures are designed to have lots of copies or support features like erasure coding to provide large capacities with good durability. But typically, all of that architecture comes at a low latency performance overhead. So So we'll talk a little bit now about some of the storage layers within a storage system. So we said before that some of the different data access interfaces are well understood in terms of the attributes that they have. But one thing that needs to be understood is that the storage systems have lots of different layers in their environment, and very often the way that you consume the storage doesn't necessarily determine the underlying architecture of that storage. And more with automation and cloud-native environments, it's often you often come across scenarios where different storage systems are layered on top of each other. So, for example, it's not unusual to see a file system layered on top of an object store, in which case it will have the sharing capabilities of a file system, but the latency attributes of an object store, perhaps. And there are other examples where perhaps a block store is presented from a distributed file system, where again, just because it's being consumed as a block store doesn't necessarily mean it has the attributes of the block store. It has the attributes of the underlying system. So, starting at the very top of that layer, we have a number of abstractions that are applied by the orchestrator and the operating system. And indeed, some of these things can definitely affect or contribute to the availability or scalability or performance of these systems. So in the case of volumes, you have things like volume managers, which can balance workload across a number of devices. But also in the API side of the world, there are a whole set of things that can be influenced by the orchestrator to provide things like discovery and load balancing and integrate with service meshes and ingress controllers, etc. The topology of the actual storage system is also important to consider. This can change just about every attribute of a storage system. We have storage systems that are more traditional, where they have a centralized architecture, and you have a number of systems that connect to a central point. These sort of systems tend to be systems that scale up as opposed to scaling out. So they tend to be systems that perhaps offer lower latency capabilities, but not necessarily good scaling capabilities. You have, on the other hand, you have distributed storage systems, where the topology of the storage system is made up of a number of different components that can be distributed within an environment. These tend to have better scaling and better capacity attributes, typically at the cost of some of the performance or the latency capabilities. There are also systems very often seen in some of the database systems that provide sharding capabilities, where effectively you have multiple instances of a storage system, and different components of the data set are sharded to different systems within the different components. This can provide some easy scaling capabilities, but also has quite large operational overheads if your workloads change or your data sets change. And finally, one thing which is quite common in a number of cloud-native workloads is a hyperconverged storage topology. So in a hyperconverged topology, which is perhaps fairly common in software-based storage systems when they're automated by an orchestrator, you just have nodes within your cluster, and those nodes can be used both to consume storage as well as provide storage services. So there are some advantages in that. There's obviously a simplicity elements to this, but then there might be other commercial or operational challenges to that sort of topology. Data protection is another layer within a storage system. So different storage systems can protect data in different ways, typically through some form of redundancy. There are the more traditional systems that might be protecting data through a RAID or some sort of mirror where data is protected by parity or copies. Erasure coding is a technique which is used in some distributed systems and very commonly found in object stores. And erasure coding allows you to create multiple sets of parity across a data set. And this can be used to give you really good durability, but typically comes at additional CPU and performance overheads. And then finally, replicas are quite a common concept now with cloud data storage, where rather than protecting the data on individual hosts, we're talking about creating replicas across different hosts to protect against, say, host failures or individual node failures. Storage systems also provide a number of different data services. And those data services tend to complement the rest of the storage system, but can actually be key to the architecture and to the patterns that you're defining within your application. So things like replication, where perhaps a storage system might give you protection across availability zones or different geographic areas. Things like snapshots and clones, which can provide data management and data copy management functionality to provide you with the ability to take point-in-time copies of data, which can be used for things like backups, but also for services like test to production promotion and data lifecycle activity. And then finally, encryption. So we were presenting. We had a cloud native storage day on Monday. And we had a number of end users contributing different advice and examples of their use cases. And one of the repeating trends was that storage systems focused on performance and reliability initially in cloud native environments, but more and more security and encryption are kind of becoming de facto standards that need to be enforced. So in much the same way that network connectivity is always encrypted with TLS, it's getting more and more commonplace to have encryption and storage key management for that encryption as part of the data services that a storage system works with. And then finally, and I'm not going to talk much about this, there's obviously at the end of every storage system there's some physical store somewhere that actually where all the bits actually land. Traditionally, that's been spinning disk, but more and more we're working with flash storage and solid-state storage. But we should also consider some of the caching capabilities that the storage systems provide, because this can be quite important in terms of consistency discussions within a storage system. So that was all about the data access interfaces. I want to talk a little bit now about the management interfaces within a storage system. So the management, the orchestrator can have a number of different ways of interacting with a storage system. The workloads themselves will be talking to the data plane in a storage system, whereas the orchestrator will be interacting with the control plane. There are a number of different control plane interfaces which have standardized over time, such as CSI, which is the container storage interface. There's DVDI, which is the Docker volume interface. There are Flex drivers in Kubernetes as well as native drivers. And with all of this, there's also a set of frameworks and tools that have evolved to help provide additional functionality or help facilitate interactions between APIs, between orchestrators and the storage systems. So projects like OpenSDS and Rook fall into this category, for example. The interfaces that are available in Kubernetes primarily today are the native volume drivers, which are drivers that are sort of mainlined into the main Kubernetes source. But the standards that Kubernetes is moving towards is CSI. So CSI stands for Container Storage Interface, and in much the same way that we had CNI for networking and CRI for the runtime, CSI attempts to provide an abstraction mechanism between Kubernetes and the storage systems. It's probably worth pointing out that CSI isn't a Kubernetes-specific technology. It is actually container orchestrator agnostic, and other orchestrators like Mesosphere, for example, and Cloud Foundry also have CSI interfaces. But I guess the more mature, well-known ones are the interfaces between CSI and Kubernetes. On that, I will stop here for a second and ask if the audience has any other questions before we talk a little bit about some of the next steps that the that the Storage SIG wants to work on in the future. Nothing at all? Don't be shy. Okay then. Well, that was easy. So finally, I just want to end my presentation to talk a little bit about some of the things that we're going to be working on next with the Storage SIG. So we have launched a storage survey to the end user forums of the CNCF, but we would also encourage any of you that have the time to provide feedback to fill in the survey too. The information that we're looking for is the types of challenges that you're coming across in cloud-native storage environments, and the areas where you think more information or better projects would help. We're also going to be looking to provide some real-life use case information for a handful of different traditional scenarios to help provide better information on how cloud-native storage is actually consumed in the real world. And we're also looking to author a set of papers to help end users evaluate the different attributes of a storage system. So we're looking to start off with performance and availability as the starting areas, and looking to document some of the traditional tools that are available in this area to provide you with the capabilities of evaluating the different storage systems that you might be looking at yourself. And finally, I'd encourage you all to get involved. The CNCF SIG storage is open to the public. We'd love to hear your thoughts and comments in our weekly meetings, and we'd love to help you get involved in different projects and different papers. And if any one of you would like to get in touch direct, all of the chairs and tech leads are available on both the CNCF and the Kubernetes Slack, so as well as the mailing list. So feel free to get in touch and suggest any options. Any questions now? Woohoo!
I'll give you like a 16-part question. So can you kind of articulate the difference between a sandbox project and an incubator project, and what the CNCF, does for, something that's a sandbox or an incubator, and at which point it graduates to become endorsed by the CNCF?
Yeah, so this is a good one for a good segue to introduce Quentin, who helped write some of those graduation criteria.
Hi, I'm Quentin. I was formerly on the TOC and helped formulate some of that stuff around the sandbox. So the answer to that question is, the sandbox is explicitly there to create a neutral environment where multiple companies and individuals can collaborate in a safe place And in that way, it does not actually imply that the technology is stable or usable in production or in any way like technically endorsed by the TOC. In many cases, some of these projects barely exist when they come into the sandbox. They just need a home where they can explore ideas or develop technology collaboratively between companies. So that's the idea of the sandbox. And there's a variety. I mean, there are some projects in the sandbox that are fairly mature, but we don't, as a CNCF, we don't actually kind of tell you to go and use these things. However, the incubation projects go through a very substantial technical due diligence by the TOC and the SIGs. They're not necessarily like fully production ready yet, and there are a couple of caveats around incubation projects which you need to be aware of. For example, they may still have one major contributor company. So, you know, if that company goes out of business or in some way decides to dump that project, that is a risk that still exists with incubation. So this is typically the phase where those projects are trying to get, you know, healthy balance of collaborators across multiple companies. They also possibly used only used in production in a, you know, relatively small number of companies. They are used in production. They do. In order to be an incubation project, your project has to be used in production in several places, but it may not be, you know, widespread, used in a widespread way. And then obviously graduation is one step above incubation again. And that's, you know, Kubernetes is the kind of poster child for that. You know, tons of people use it, tons of companies contribute. If any one of the companies actually pulled out, if Google were to, you know, I'm making up stories, but if Google were to go bankrupt tomorrow, you know, Kubernetes would still be there. There's still tons of other people who understand how Kubernetes works and would continue to maintain it into the future. Does that answer your question?
Any other questions?
So my question now, what's the difference between me contributing to your SIG or me contributing to a project hosted by this SIG? Does that make sense?
Sure. So it's probably worth pointing out the SIG doesn't host the projects. The SIG helps the projects or helps review the projects and seeks out new projects and, you know, provides information to the TOC to, at the end of the day, for the TOC to make their decision on a project. So you contributing to the SIG helps with the work that the SIG is doing in terms of perhaps reviewing those projects or working on some of the white papers or some of the information that we're working on. If you're obviously contributing to a project directly, well, then you're helping that specific project. And there, you know, there's you know, unlike the, you know, things like the Kubernetes SIGs that are working on specific projects, we're here more as facilitators to help the TOC scale as more vendors and more projects and more organizations join.
They're struggling. They can't turn the sound up anymore.
Okay.
So you need to speak louder.
Okay. Sorry, was everyone hearing that, or do I need to repeat? We're good? Okay. Any other questions? No? Okay. Well, in that case, have a good rest of KubeCon, and thank you all for attending.